Welcome to this session of maths. Today we are going to look at numbers. To begin with, let's understand our numbers. So numbers can be broadly categorized as shown. So this is a Venn diagram that gives you all types of numbers. Try to remember this diagram. So basically numbers have been grouped in two types: rational numbers, irrational numbers. And basically even before that, so this box is real numbers, right? Near numbers are basically the numbers that can be represented on the number line, right? The other type of numbers are complex numbers. Now this is not going to be this is out of the scope of the GRE, but for the sake of understanding we'll see this. So complex numbers are basically numbers that do not lie in number line. They lie somewhere outside number line. So and they involve root of negative numbers. So if you studied mathematics, you will know the root of -1 is considered I, and these numbers are imaginary numbers. So we'll not look at these numbers. They are not important with respect to the GRE. So we'll look at real numbers. This box represents real numbers. Real numbers are again split into rational numbers and irrational numbers. Rational numbers are the numbers that can be written in the form P by Q, where P and Q are integers. Whereas irrational numbers are the numbers that cannot be written as P by Q. We'll look at irrational numbers later. Just try to understand the categorization here. So in rational numbers also, we have the counting numbers are also numbers that we call natural numbers. So they start from 1, 1, 2, 3, 4, 5, 6, 7. Add a 0 to that, you get whole numbers. So we have 1, 2, 3, 4. This is whole numbers. This is counting numbers. You add a 0 to that, you get whole numbers. And include the negative numbers to this, and you will get integers. Right? Rational numbers are also fractions because they can be written as P by Q. So this is basically the categorization of numbers. Let's look at some basic definitions. Divisibility. So when we say x is divisible by y, what do we exactly mean? So x is divisible by y. That means when I divide x by y, I get some whole number. I don't get any remainder, right? Let's say for example 15 is divisible by 5 because 15 by 5 is 3, remainder is 0. So that means 15 is divisible by 5. So technically the definition is divisibility is the ability to divide one number by another number with no remainder. This is the most important part. If you divide 16 by 5, we'll get 3 as quotient and 3 into 5 plus 1 as the remainder. So 16 is not divisible by 5. Examples: 10 is divisible by 1, 2, 5, 13 is not divisible by 4. That way. What are multiples? Same concept, just that we look at it in a different angle. A number that can be divided by another number without a remainder. Right? So multiple of 5 is going to be 5, 10, 15, 20, like that. Because all these numbers when divided by 5 don't leave any remainder. Right? So 10 is a multiple of 1, 2, 5. Look at this. The same concept, same statement written differently. 13 is not a multiple of 4. That means 13 is not divisible by 4. There can be infinite number of multiples for any given number. You take any number, you take 15. Let's say so we're going to have 15, 40, 45, 60, like that. We can go on till infinity. There are infinite number of multiples. And what are factors? Another related concept. Factors are the numbers you multiply together to get another number. So let's say 1, 2 and 5 are factors of 10. That means 10, if you split it as product of different numbers, we're going to get it like this, or 2 into 5 or 5 into 2. Correct? So look at it. So we have 1, as a factor, 2 and 5 as a factor, here also 2 and 5 as a factor. So the comprehensive set of all factors is going to be 1, 2 and 5, and of course the same number itself. So 1 will always be a factor, the same number will always be a factor, right? So these are called factors. How is it related to multiples? If 2 and 5 are factors of 10, that means 10 is a multiple of 2 and 5. So it's the same relationship we are looking at from a different angle. Same thing, 4 is not a factor of 13 because 13 is not a multiple of 4. Or other way of saying is 13 is not divisible by 4. Factors of a number are always finite while multiples of a number are always infinite. Important statement. Factors of a number are always finite. You take any number, let's say 100, you can always split it down to, let's say this is going to be 2 into 5 into 5. Sorry, 2 into 5 into 2 into 5. Correct? So there is always going to be a finite set of factors for any given number, right? Whereas the multiples of a number is going to be infinite, that we just saw in the last slide. So just remember this point, factors of a number are finite while multiples are infinite. The least common multiple of two integers is the smallest positive integer, that is multiple of both. So if you are talking about, this is called the LCM. So if you are talking about, let's say two numbers, 15 and let's say 25. So let's just factorize. What we do is 15 is 3 into 5, 25 is 5 into 5. Correct? So I need a least common multiple. So I need the smallest, least means smallest, common multiple. Okay. So I need a multiple of 15, I need a multiple of 25, and I need the smallest such multiple. So what I do is, I will take the highest power of all the factors involved here. These are prime factors. What exactly are prime numbers, we'll see in the next slide. But in fact, just to explain how this LCM works, these are prime factors. So what we do is, we write it in this fashion, into 5 raised to 1, and this is 5 raised to 2. So what we do is, we take the highest power of every prime factor. So we take 5 raised to 2, we take 3 raised to 1, and we multiply them together. What we get is 3 into 25, 75. So 75 is the least common multiple of these two numbers. Greatest common divisor is common divisor, and it is the greatest. So it is the largest number which is a common divisor of both. So let's look at these numbers again. 15, 25. 15 is 3 into 5, 25 is 5 into 5. So what I will do now is, I'll again write it in this fashion. But now because I need a common divisor, so I'm only going to take numbers or powers of numbers that are common in both numbers. So 3 is not common in both, right? And 5 raised to 1 is common in both, but 5 raised to 2 is not common. So I cannot take 3 raised to 1. I cannot take 5 raised to 2 because that is not common. The only thing I can take common is 5 raised to 1. So just GCD, or it is also called the HCF, highest common factor, is going to be 5 raised to 1 equal to 5. So both GCD and LCM require you to do prime factorization, and there are different ways of calculating. GCD, one trick that you need to remember is, GCD is the greatest number, common divisor, but because it is the divisor, it is going to be, or rather because it's going to be a factor, it is going to be smaller than both the numbers, whereas it is LCM is a multiple, so it is going to be greater than both the numbers. So let's move on to divisibility rules. So there are some standard rules that will help you decide whether a given number is divisible by certain numbers. So divisibility by 4, it means that the original number has to have a last digit as 0, 2, 4, 6 or 8, or rather it should be an even number. In fact, the definition of even number is that all the numbers divisible by 2 are even numbers. So if we are talking about numbers such as 8, last digit is 8, so it's an even number. 20, last digit is 0, so it's an even number. Pretty straightforward. Divisibility by 3, the sum of digits is divisible by 3. Let's say, talking about this number 389, you do 3 plus 8 plus 9, what you get is 20. Okay. 20 is not divisible by 3, or rather 20 also you can do 2 plus 0, ultimately you will get 2. So 2 is not divisible by 3, so 389 is not divisible by 3. Now here itself, in another trick in this specific example is that this is 389. So you know this is divisible, this is divisible. Anyway, we are going to add. So all you have to worry about this 8, and you know that 8 is not divisible by 3. So immediately by looking at the number itself, you can say that it's not divisible by 3. Divisibility by 4, the last two digits are divisible by 4. Now look at this. Let's take the same number 389. You know what we do is we split the number into hundreds and hundreds and ten and unit places. So we write it as 300 plus 89, right? And we are worried about whether this is divisible by 4. So rewrite it 300 by 4 plus 89 by 4, right? Now 304, or rather anything here, is going to be a multiple of 100. This piece is going to be a multiple of 100. This is always going to be divisible by 4 because 100 is divisible by 4. So all we have to worry about is last two digits. That is why what we do is just take the last two digits and see if they are divisible by 4. Divisibility by 5, pretty straightforward. The last digit has to be either 0 or 5. Divisibility of 6, the number has to be divisible both by 2 and 3. Look at this one now. This is pretty interesting. What it says is, in order to decide divisibility by 7, what you do is you double the last digit and subtract it from the rest of the number, and if the answer is 0 or divisible by 7, the original number is divisible by 7. Let's take an example. Let's say 49. So we already know 49 is a multiple, so this method should give us the same result. So what we do is we consider 4, we split this number, rather you take the unit number separately and this piece separately. 4 minus double of the last digit, 4 minus 18. What do we get? We get minus 14. So minus 14, forget about this negative sign, but 14 is going to be a multiple of 7, right? In fact, minus 14 is also multiple of 7. Minus 14 is minus 2 into 7, that way, right? So this we are getting a multiple of 7. So this number, original number 49, would be a multiple of 7. Let's take another example. Let's take a big one actually. Let's say 4973. Okay, just some random number. Now you will notice, see, 49 is multiple of 7. So 4900 is going to be a multiple of 7. 4970 is also going to be a multiple of 7. That means 4973 is not going to be a multiple of 7. Right? So let's see if we get the same number. What we do is we consider 497 minus 6. Right? 3 into 2 is 6. We get 491. Now subsequently, for 491 also you do the same logic. What we do is we do 49 minus 2. What we get is 47. Now 47, we know that it's not going to be a multiple, but if you want, you can still go ahead. What you can do is you can do 4 minus 14, which is going to be minus 10, right? Until you get so you can keep continuing to doing this actually, but now at least at this point or this point, you can conclusively say that this original number was not a multiple of 7. So this is a little tricky. Just try to familiarize yourself with this. Divisibility by 8, the last 3 digits have to be divisible by 8. So similar logic, what are we doing now? Let's say we are talking about this number, right? So what are we saying is, I split it into thousands. So I say 8000 plus 383 and I divide it by 8. Now this piece, 1000 divided by 8, is always going to give us a whole number because 1000 is divisible by 8. So this part we don't have to worry about. All we have to worry about is last 3 digits, right? So pretty similar logic as we did for divisibility by 4. Divisibility by 9, the sum of digits is divisible by 9, pretty similar to what we saw for divisibility by 3. Okay, divisibility by 10, pretty straightforward, number has to end in 0. 11. This is a tricky part. The difference of sum of digits at odd places and sum of digits at even places has to be either 0 or divisible by 11. So let's look at this number 121. What we do is we will consider sum of even minus sum of odd. So how many even numbers we have? Rather, how many even numbers at even places? Right, even digits. So we are talking about this second digit, then this digit, then one digit here, then this digit, that way. We are not actually bothered about whether the specific digit is even or odd, right? So even places. So I have only two. Here I have two odd places, first, second, third, that way. So I am going to have 1 plus 1, 2. I am taking the difference. 1 plus 1, 2. So 2 minus 2 is going to be 0. So I get a 0, that means 121 is divisible by 11. Let's take another number. Let's take a big number. Let's say 33396. Now you will know that this number is not going to be divisible by 11, because if you look at it, or rather it will be. So if you actually do 33396 divided by 11, what are you going to get? You're going to get 3, then you're going to get 0, then you're going to get 3, and then you're going to get 6. Correct? This is going to be the quotient. There is not going to be any remainder. So that means this logic should give us the same result. Let's see. I add up 9 and 3, so that is 12, minus I add up 3 plus 3 plus 6, that is again 12. So 12 minus 12 is 0. I get a 0, that means this number got divisible by 11. So this is very similar to what we did for divisibility by 7. Divisibility by 12, the number has to be divisible both by 3 and 4. 3 and 4 because 3 and 4 are factors of 12. Let's look at prime numbers. So prime numbers are numbers that have only two factors, 1 and itself. So we have already seen that a number will always have factor as 1, a number will always have itself as a factor. But if it does not have any other factor, then it's a prime number. So it's very, very basic type of a number that cannot be split further. So let's say 2, 3, 5, 7, 2. How can we write 2? 2 is always going to be written as 2 into 2. Whereas 4, it can be written as 2 into 2. So that means that if you look at all the factors of 4, the set is going to be 1, 2 and 4. Correct? So it has 1 as a factor, which any number will have. The number itself has a factor, any number will have. But there is another number which is also a factor of 4. So 4 is not a prime number. Whereas if you look at, let's say 7 has only two factors, 1 and 7. So 7 is a prime number. 2 is the only even number that is prime. Very important. 2 is the only even number that is prime. That is because any other even number, let's say 16, is going to have 2 as a factor. Correct? And because there is going to be 2 as a factor, this number cannot be prime. So 2 is the only prime number. Difference between odd primes is always even. Correct. So there is only one even prime number, rest all other prime numbers are odd, right? And difference between any two odd numbers is going to be even. So difference between any odd primes is always even. Composite numbers that are not prime are called composite numbers. So any other number. So here we have seen 4 is not prime, so 4 is composite. 16 is not prime, so 16 is composite. 0 and 1 are not prime, nor are they composite. Now this is a very special case. 0 and 1 are not prime, nor are they composite. Why this is so? This is beyond the scope of the GRE, but try to remember that 0 and 1 are not to be counted as prime or also as composite. Co-primes, a pair of numbers not having any common factors other than 1 or minus 1. So let's say 15 and 28. Let's first split 15. So 15 is 1 into 15, which is 2 into, there's no 2 is not, 15 is not divisible by 2, so it is 3 into 5, and then 5 into 3. So that means the factors are going to be 1, 3, 5 and 15. correct? 1, 3, 5 and 15. Let's look at 28. 28 is 2, 1 into 28 obviously, 1 into 28. So 2 into 14. Also 14 can be split into 2 into 2 into 7. Is 28 can also be written as 4 into 7. Correct? So let's take all these together. What do we get? This is the set of number. Yes, 28 can also be written as 2 into 14. Correct. So these are all the factors. Now what we'll see is we'll see how many factors are common. So 1 is common. In fact, 1 will always be common, right? 3 we don't have here, 5 we don't have here, 15 we don't have here. So only 1 is common. So these two numbers 15 and 28 are co-primes. They are not prime numbers, but they are co-primes. Co-primes means they are prime with respect to one another, relative primes, right? So they are co-primes, a pair of numbers not having any common factor other than 1 or minus 1. What is prime factorization? Now this is a very important concept. Based on this, there are a lot of type of questions that are asked on the GRE. So please pay attention. Prime factorization is the process of finding prime factors of a number. It is factorization. So we are splitting the number. We are splitting the number into prime numbers. So basically I am getting all the very basic components of the number that are prime numbers. Okay. So let's say 100. 100 we can write it as 1 into 100, right? Are both these numbers prime? No. So that means 100 is composite. That means 100 can be split further. So let's split it further. So what we do is, we don't have to write this 1 will always be there. So we write it as 2 into 50. So 2 is prime, fine. Is 50 prime? No, it is not prime. So let's split it further. So 2 into 2 into 25. Correct? Now I split 50 further. 25 is also not prime, so I keep splitting 2 into 2 into 5 into 5. Correct? Now all the numbers are prime. So I end up getting 100 as 2 raised to 2 into 5 raised to 5. So this process is called prime factorization, and 2 and 5 are called prime factors of 10. Another example, prime factorization of 73. 73 is only one. 73 in itself is a prime number. So there is only one way we can express 73, 1 into 73. So prime factorization of a prime number is like this, 1 into the same prime number. Some basic rules. Factor foundation rule. It says that if x is divisible by y, so that means whenever you say x is divisible by y, we can write it as x is equal to y into k, or some number. But this number will be a whole number, or an integer rather. This number will be an integer. So x is divisible by y and y is divisible by z. So we write it as y is equal to divisible by z means it is z into, let's say, k2. This is k1, this is k2, right? So it says that x is yk, yk1, y is equal to z k2. So we can write it as x is equal to k1 into y, which in itself is z into k2. So we'll see that x is equal to k1 k2 some constant into z. So x will also be a multiple of z, or z will also be a divisor of x. So the same thing is written here. If x is divisible by y and y is divisible by z, then x is divisible by z. So that means x will also be k1 k2 divisible by z. So pretty intuitive. If you add or subtract multiples of x, then the result is also a multiple of x. Let's say I have this first multiple of x, second multiple of x. This is, let's say, multiple of x. That means it is going to be of the form k1 times x. This is going to be of the form k2 times x. So I add them. Let's say x1 plus x2. So what do? So I get k1 times x plus k2 times x. So I get k1 plus k2 times x. So k1 plus k2 times x, this is a fixed number. So that means x1 plus x2 can also be written as a multiple of x. So that means k1, x1 and x2, x1 plus x2 is going to be a multiple of x. Same thing, x1 minus x2 is going to be k1 minus k2 times x. So x1 minus x2 is also going to be a multiple of x. So if you add or subtract multiples of x, then the result is also a multiple of x. Remainders. If x is divided by n producing quotient q and remainder r, then x can be written as n into q plus r. Let's look at this. 15 divided by 6, let's say. So what do we get? We get 2 as quotient and we get remainder as 3. Correct? So how can we mathematically relate 2, 3, 6 and 15? We write is 15 is 2 times 6, that is the quotient, plus 3. Correct? Same thing here. Here 15 x is getting divided by n. There are q times full n and there is a remainder of r. So this becomes the mathematical expression of division. Remainders range from 0 to n minus 1. Obviously, if your x is a multiple of n, so we are going to have x is equal to k1 times n. k1 times n divided by n, we are going to get some whole number. So remainder there is going to be 0. The remainder will range from 0 to n minus 1 because it cannot go more than n, because if it goes above n or becomes equal to n rather, then that means there will be an 1 will get added to the quotient and the remainder will become 1. For example, if you're talking about say 15 by 3, so we get remainder as 3, right? We just saw that. Now let's say if you do 15 by 6, we get remainder of 3. 16 by 6 will get a remainder of 4. 17 by 6 will give us a remainder of 5. Now 18 by 6 will give us a remainder of 0. 19 by 6 will give us a remainder of 1 again. So you will see that after 5, that means after n minus 1, immediately the next remainder comes out to be 0, because now here the quotient here the quotient was 2, here the quotient was 2, here the quotient was 2. Suddenly the quotient becomes 3 and remainders become 0. So you cannot have a remainder greater than n minus 1. Addition and multiplication law for remainders, pretty straightforward. The remainder of a sum of two numbers, so I am talking about x plus y divided by n, and I am talking about the remainder of this, is given by sum of their remainders. So remainder of x plus y divided by n is remainder of when x is divided by n individually plus remainder of when y is divided by n individually. Let's look at this. We are dividing by 3, remainder 15 with respect to 3 is 0, right? Remainder 10 with respect to 3 is 1. So now what I do is I take this 15, original number 1 plus original number 2, I add them up. So I am interested in finding out remainder of 15 plus 10 with respect to 3. So using this logic, what I get is I am just going to add the individual remainders with respect to 3. So individual remainders are 0 and 1 of these two numbers. So ultimately for 15 plus 10 also I should get remainder of 1, and you will see that 25 plus 25 remainder 3 is going to give you 1. Right? You can prove it. I encourage you try to prove it by simple algebra. You can the way to do that would be you write this original number 1, let's say n1 as some quotient into x1 as some quotient into n plus some remainder, right? X2 as some quotient into n plus remainder 2. You add them up and divide it by n, and you try to get it of the form x3 is equal to q3n plus r3, and you will be able to relate that r3 is equal to r1 plus r2. So I leave it up to you for homework. The remainder of the product of two numbers is the product of their remainders. Pretty much the same thing. Remainder of 5 with respect to 3 is 2. Remainder of 10 with respect to 3 is 1. So when I am multiplying these original numbers 5 into 10 and trying to figure out the remainder of that with respect to 3, so that is going to be product of individual remainders. So that is going to be remainder of 50, which is product of 5 and 10 with respect to 3 is individual remainders product. So 2 into 1 is equal to 2. Again, you can do x1 is equal to q1n plus r1. You can take x2 is equal to q2n plus r2, and you try to figure out x1 into x2 in the form of some q3n plus R3, and you will see that R3 is going to be R1 into R2. Let's move to the next concept now, odds and evens. Pretty straightforward. Even numbers are divisible by 2, odd numbers are not divisible by 2. Even and odd numbers are alternate. And addition and subtraction of evens and odds. Odd plus odd is going to be even. So you always, for these rules, you always write it as odd is equal to even plus 1, that way. So if you do odd plus odd, you are going to get even plus 2. So that means even plus 2 is going to be even. So odd plus odd is going to be even. Even plus even is always even. Odd plus even is going to be odd, right? So just remember that for the product, for the sum to be odd, there will have to be exactly one odd number in it. Multiplication, just remember that if there is going to be even one even integer, the whole product is going to be even. So even plus anything is even. Even plus into even is even. Odd into even is also even. Odd into odd is the only possibility where the product is odd. Division by evens and odds, these are the same rules, just that we are looking at them at different angles. So even by even is going to be even, or odd, or even integer, because even by even is like this. Even by even is equal to something. That something can be odd also, because odd into even will ultimately give us even. So it can be anything. It can be even into even giving even, or even non-integer into even also giving us even. So this is very open-ended. Even divided by odd. So we are talking about even divided by odd. What can we say about this number? This number cannot be odd, because if it was odd, it would have been odd into odd, would have given us odd. So this number can be even, this number can be non-integer also. Odd divided by even, odd divided by even is always going to be a non-integer. It cannot be even, because then even and even would have become even. It cannot be odd, because odd into even would also have become even. So it will have to be non-integer. Odd divided by odd is always odd or non-integer. Odd divided by odd cannot be even, because if it was even, it would have been even into odd, would have given us even. So it cannot be even, it can be odd, or it can be non-integers also. So you want to remember all these division by evens and odd rules. So let's look at this practice problem. Please pause the video and give it a try. What is the last digit of 36 raised to 67, last digit of 52 raised to 56? See, this is last digit problem. The trick here is that, so whenever we are dealing with the last digit of a power, an exponent rather, you always only consider the last digit and consider this power. So this is going to be last digit of this number is going to be last digit of 6 raised to 67. Obviously 6 raised to 67, 6 raised to anything will always going to end in 6, right? So here the last digit is going to be 6. You can verify it for yourself. 6 into 6 is 36. Again you get a 6. 6 into 6, 36 into 36. Again we are going to get 6. Multiply that by 6, 36 again. You are always going to get 6. So 6 raised to anything is 6, right? Same thing here. We are only interested in 2 raised to 56. Now look at this. If you tabulate the powers of 2, you are going to get 2 raised to 1 as 2, 2 raised to 2 as 4 last digit, 2 raised to 3 as 8 as last digit, 2 raised to 4 6 as last digit, and then 16 into 2 is going to be 32, 2 again. So you will see that for every power, it is the same numbers that are repeating, and the cyclicity is 4. In fact, for all numbers the cyclicity is 4. There are some numbers for which cyclicity is 2. There are some numbers for which cyclicity is 1. Like for example 6 cyclicity is 1, 4 cyclicity is 2, in the sense that 4 raised to 2, 4 raised to 1 is 4, 4 raised to 2 is 6, 4 raised to 3 is again 4, last digit, correct? So cyclicity is 2. But for as a universal rule, we take cyclicity as 4. So now depending on where this power falls, so if power falls here, 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 or here, or here, or here, here, we are going to have only one of these digits as the last digit. So where does this 56 fall? So we'll basically have to consider 56 remainder of that with 4, correct? So it's going to basically fall 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, that way. So that means 56 remainder by 4 is what we are interested in. So 56, you will know that 56 is multiple of 4, so remainder is going to be 0. That means basically 56 is going to end up here in this bucket. 1, 2, 3, 4, 5, 6, 7, all multiples of 4 are going to end in this bucket, in which case the last digit of 2 raised to anything, any power that leaves a remainder of 0 with respect to 4 is going to be 6. So here also we are going to get last digit as 6. So here we get 6, here also we get 6. The answer is C. Once again, whenever we were dealing with last digit number, we only consider last digit of the base. So 6 raised to 67. We consider cyclicity as 4. We look at this power number. We take a remainder of that. So here the remainder is going to be 3. So 6 raised to 3. Last digit of that is going to be the last digit of this entire number. Correct? Now anyway, for special case is 6, because 6 raised to anything is 6. So we don't need to do this process. But for any other number, this is how we do the process. Let's move to this problem. Please pause the video, give it a try. Five, 9, 6, 4 is divisible by 6 and 7. It is already given. You don't need to verify that. Already divisible by 6 and 7. What is the next integer after 5, 9, 6, 4? That is also divisible by 6 and 7. Okay. So basically, if you understand this question, what it is saying is 5, 9, 6, 4 is equal to some multiple of, let's say, k multiple of when it says divisible by 6 and 7, so that means it is some multiple of the LCM of 6 and 7, right? Correct. Now we need to add, we need the next multiple, that is also divisible by 6 and 7. That means we are talking about k plus 1 times LCM of 6 and 7, correct? That means basically we need to add LCM of 6 and 7 to this number. That number will be k plus 1th time LCM of 6 plus 1. So LCM of 6 plus 1 is going to be 6 is equal to 2 into 3, 7 is going to be 7. So we take the highest power of all the prime factors. So we take 2, we take 3, we take 7, all ones. So what we get is 42. So 42 is the LCM. We add 42 this number. So what we get is 6060. Correct? 6006 is the number. That is the next number after 5964. That is divisible by both 6 and 7. Let's look at this. Please pause the video and give it a try. What is the remainder of division of 8 raised to 2012 divided by 7? Okay. So we know that, see, from the remainder rule, we have seen that x1 into x2, the remainder of that with respect to n is remainder of x1 with respect to n into remainder of x2 with respect to n. We have seen this, right? And let's write 8 raised to 2012 in this format. So we are writing remainder of 8 raised to 2012 with respect to 7, which is 8 into 8 into 8 into 8, like that, 2 raised to 12 times, sorry, 2012 times, is equal to remainder of 8 with respect to 7 into remainder of 8 with respect to 7. Like that we will go for 2012 times. Correct? The same rule applied here. So remainder of 8 with respect to 7 is always 1. So 1 into 1 into 1 into 1, like that I am doing 2012 times. No matter how many times 1 into 1 into 1 is always going to give me 1. So the remainder here, the answer of this big expression 8 raised to 2012 divided by 7 is going to be 1. We use the remainder multiplication rule. Let's look at this one. Please pause the video and give it a try. So remainder of this, we know remainder of 2 raised to 2012 with respect to 3 can be written as remainder of 2 raised to 2 with respect to 3 the whole raised to 2012. So 2 with respect to 3, remainder of that is going to be 2. So now we are interested in this number. The remainder of this number is going to be the remainder of this. Now you will see that we got the same number here. So no matter how many times you do this process, you are always going to end up with this number. So how do we go ahead now? So we use the same formula or same method rather, but instead of we call it remainder of 2, we'll call it remainder of -1, which is technically the same thing, mathematically is the same thing. So but by using -1, now we'll be able to come up with some number here. So -1 raised to some even number is going to be 1, correct? So now we are able to get a number that is not the same number that we began with, right? So here again the remainder of 2 raised to 2012 with respect to 3 is also going to be equal to 1. We did not use remainder of 2 in this process because by doing that we were getting the same number, correct? But that doesn't help us. So we selected, instead of 2, we selected remainder of a negative number -1, and -1 raised to odd even power, we got 1, and 1 helps us conclude that the remainder of this big number is going to be 1. Let's look at this. Please pause the video and give it a try. What is the minimum value of x for which 3 raised to 3 is a factor of 3x factorial? Okay, so we are talking about 3x factorial, 3 raised to 3, which can be written as 3 3's into some integer. Let's call it I. Okay, so we need an expression like this, and we need to find out the minimum value of x for this. So that means let's look this factorial. Let's do the factorial first. 1 2 3 4 5. Let's see, these are the numbers that we are considering for value. Let's not sure if x will fall in this range from 1 to 10, but for the sake of understanding, this is how we should start. So 1 factor is going to be 1, 2 is going to be 2 into 2, 3 factor is going to be 3 into 2 into 1. So I am just writing the prime factorization here, right? So which will make it easy to understand, right? And obviously we can continue like this. Now let's look at this. If you're talking about 3 factorial, there is only 1 3 in there. Talking about 4 factorial, there is only 1 3. 5 factorial, there is only 1 3. 6 factorial, we are going to have 2 3's, right? But in that factorial, we actually need 3 3's minimum. So we'll have to go till 9, correct? Now when we talk about 9 factorial, so 9 factorial, I talk about this 3 into this 3 into these 3. So basically I have 4 3's now, and I have some other number which is basically this 1 into 2 into this 2 into 2 into this 5 into 7 into 2 2 2, that way, right? So some whole number I have, some integer I have here. Okay, now this is the number where, or rather this is the smallest number, 9, wherein I have 3 3's, correct? And that is what this question asks. What is the minimum value of x for which 3 raised to 3 is a factor of 3x factorial? Now here 3x, it is asking about value of x, and 9 factorial, the factorial, the number of which the factorial has been taken is 3x. So that means 3x is equal to 9. That means x is equal to 3. As x is equal to 3 is the minimum value of x, such that 3 raised to 3 is a factor of 3 into 3 factorial, correct? So answer here is x is equal to 3. Let's move to this problem. Please give it a try. Positive integers m and n leave remainders of 3 and 4 respectively when divided by 6. So let's write it. M leaves a remainder of when divided by 6, it leaves me a remainder of 3. It has some quotient. N when divided by 6 leaves me a remainder of 4. This is mathematical expression. We don't know the value of k1 and k2. Okay. What is the remainder when mn is divided by 3? Right? So mn, let's look at mn. Mn is going to be 6k1 plus 3 into 6k2 plus 4. So that is going to be 36 k1 k2 plus this into this is 24 k1 plus 18 k2 plus 12. Correct? So mn, this is mn. Now mn is to be divided by 3. So mn divided by 3 is going to be this whole thing divided by 3. Correct? You will see that all these numbers, coefficients of all these terms are multiples of 3. That means we are going to end with a remainder of 0. Correct? So answer here is remainder is 0. Let's move to this one. Please pause the video and give it a try. So let's see. A, B, C are consecutive integers. So it is like this. These are consecutive integers. So we are going to call them like this. A plus 1, A plus 2. Right? We don't know whether A is even or odd, whether the series is starting with an even number or an odd number. We don't know that. But what we are supposed to find out is which of the following is always odd. So let's look at the first one, A plus B plus C. If you look at these numbers, we are going to get A plus B plus C as 3A plus 3. Correct? Now A could be even or A could be odd. So if A is even, so 3 into even is going to be an even number. Even plus 3 is going to be an odd number. So this is A and this is 3A plus 3. Okay. If A is odd, then 3A is going to be odd into odd, it's going to be odd. Odd plus 3 is going to be even. So both possibilities exist. We cannot always say that 3A plus 3 is always going to be odd. So this is not going to be the answer. AB plus C, let's look at it. See, you'll understand that A and B are consecutive integers, right? So that means at least one is going to be odd and one is going to be even. Which one is which, we don't know. But A and B as a product is always going to be even, correct? Because there is one even number. And C plus C we have. So C can be even or odd. Even or odd. So the entire expression can both be even and odd. So we can't really say anything. AB plus C. See, look at this. This and this is the same thing, just that we have plus 1 here. So if we are not sure about AB plus C, okay, if we are not sure about AB plus C, we can't always be sure of AB plus C plus 1 also. So this is also not false. AC plus 1. Okay, now let's look at this AC plus 1. So if A is, same thing we'll do A. If this is A and this is AC plus, AC plus B. See, if A is even, that means C is also even. So even into even is even and B is going to be odd. So the whole AC plus B is going to be odd. If AB, if A is odd, so C is also going to be odd. So odd into odd is always going to give me odd. Odd into odd is always going to give me odd. And B is going to be even in that case. So I am talking about odd plus even, which will give me an odd again. So in both these cases, no matter what A is, whether A is even or odd, AC plus B is always going to be odd, and that is what is asked in the question. So this is the answer, AC plus B. Let's look at this. Please pause the video and give it a try. The number of factors of 120 and 30. So let's first find out prime factors of 120. So 120, we know that it is 2 into 60. Correct? So it is 2 into 30, which is 2 into 2 into 3 into 10, which is 2 into 2 into 2 into 3 into 5. Correct? This is prime factorization. So this is 2 raised to 3, 3 raised to 1, 5 raised to 1. Correct. Now number of factors of 120. Now I am not worried about the prime factors. Actually, I need how many different factors can I form from these 3 2s and 1 3 and 1 5. So you will see that whenever I am taking product of anything, that means basically I have this one bucket, I have another bucket, I have another bucket. No matter how many I select from this, I take 2 2s, multiply that with 3, it's going to be a factor of 120. I take 1 5, multiply that with 3, I get a factor of 120. So any combination that I pick from here is going to be, and multiply it together, is going to be a factor of 120. So how many such combinations are possible? That is going to give me the total number of factors of 120. So let's look at it. Either I can take 1 2, or I can take 2 2s, or I can take 3 2s, 1 2 2 2s or 3 2s, or there is also a possibility that I don't take any 2, I only take 3s and 5s. Still I am going to get some factor of 120, right? So that means there are 4 possibilities here. That we have 3 2s, 1 2 is a possibility, 2 2s is a possibility, 3 2s is a possibility, no 2 is also a possibility. 4 possibilities here, 2 possibilities here. I can take the 3 or I cannot take the 3. 2 possibilities here. If I want, I'll take the 5. If I don't want, I will not take the 5. So that means you will see that it is basically all the prime factors and their powers, 1 added to those powers, and a product of all these. Why product of all these? Because how many 2s I have and how many 3s I have and how many 5s I have, those are independent. So 4 options here, 3 options here, 5 options here. What I end up getting is 4 into 2 into 2 is 16. So there are 16 possible factors of 120. Correct? These 1 and 120 are included in it, because if I don't take any 2, don't take any 3, don't take any 5, I am going to get 1. If I take all the 2s, all the 3s and all the 5s, I am going to get 120. So this is all the number of factors of 120. So that here we have 16, here we have 30. The answer is B. So whenever in fact we are dealing with a number, the prime factorization is prime 1 raised to power 1, prime 2 raised to power 2, prime 3 raised to power 4, power 3, that way. So number of factors of this n is going to be 1 added to all these powers and a product of that. Like that. Let's move to this problem. Please give it a shot. When the number of employees of an office are divided into 12 teams, there is no employee left without a team. So that means number of employees, let's say that is n, that is some multiple of 12. So n is equal to k1 times 12, 12 times k1, let's say, right? When exactly half of the employees are joined by their spouses, exactly half of the employees, that means n will have to be an even number, right? And so n minus 2 people are joined by their spouses. So one spouse individually, so that means there are another n by 2 people added to the group. So these are the half people who are not joining their spouses. These are the ones who are joining their spouses. This was the original team. and right now the spouses have been added, so n by 2 gets added. So we are basically talking about now 3n by 2 people, correct? When this 3n by 2 people are divided into 12 groups, there are some people left without a team. Okay, how many people are left? So now we are asked to find out what is the remainder of, what is this R? 3n by 2 have been divided into 12 groups, so it will get some quotient and we'll get some R. So what is this R? So let's just put n is equal to 12k1. So we get 3 by 2 into 12k1 is equal to 12k2 plus R. So what we get is 18k1 is equal to 12k2 plus R. So that means R is equal to 18k1 minus 12k2, right? Okay, so what do we need? We need this value of R. Now we have two unknowns. We don't exactly know the value of R, but let's look at it carefully. It says that there are some people left, correct? So that means there is some remainder. The remainder is not 0, correct? And now let's look at the values of k1 and k2. Let's say k1 is 1, k2 is also 1. So what do we get? R is equal to, and this is the value of R. R is equal to 18k1, so that is 18 minus k2, 12k2, so that is 12. So we get remainder of 6. Let's say R is k1 is equal to 2, k2 is equal to 1. What do we get? 18 into k1, which is 36, minus 12 into k2, which is 12. So we get 24. But we'll see that if there are 24 people remaining, which basically remainder of 24 divided by 12, so that effectively it means 0 people, right? No people remaining. Let's see, k1 is equal to 3, k2 is equal to 1. We'll see that we are talking about 54 minus 12, which is going to be again 42. The remainder is going to be 6 again. So we'll see that there are only two possibilities for remainder. Either it will be 6 or it will be 0. But we'll know that there are some people left behind. That means remainder cannot be 0. So the remainder will have to be 6. There are 6 people left behind. So let's move to this problem now. Please pause the video and give it a try. What is the highest power of 70 in 50 factorial? Okay, I'll tell you two methods of doing this. First, very fundamental method. Let's consider 50 factorial. So we are going to have 1, 2, 3, 4, 5 like this till 48, 49, 50, right? Let's do the prime factorization of all these numbers. 1, 2, 3, 4, 6 and 7, 5, 6, 7. Sorry, this is not 4, this is 2, 2. This is 2, 3. This is 7. This is 2, 2, 2, like that. So when we come to 14, we get 2, 7. Correct? I'm actually interested in 7 because 7 is a factor of 70. So 70 is basically 7 into 2 into 5. Correct? So now we'll see in the factorial, 50 factorial, which is 50 into 49 into 48, all that, we are going to see that there are going to be less 7s than 5s, less 5s than 2s, correct? Because 5 is occurring more frequently than 7 and 2 is occurring more frequently than 5. So the bottleneck here is going to be 7. So we just need to find out the power of 7, how many 7s we have, right? And those many 70s we will have, because we need 2 and 5 to make a 70. If we have 1 7, we can always assure that for a corresponding 7 we'll have a corresponding 5 and corresponding 2. There is no shortage at 2s and 5s with respect to 7, correct? So how many 7s will we have? So we'll have 1 7, 14, 21, 28, 35, 42, 49. These are multiples of 7. Here we're going to have 1 7, here again 1 7, here we are going to have 3 and 7, another 7. Here we're going to have actually this would be 2 and 2 rather. This is going to have 5 and 7. This is going to have 2 and 3 and 7. This is going to have 2 sevens. Correct. So how many sevens we will end up having in 50 factorial? We're going to have 1, 2, 3, 4, 5, 6, 7 and 8. We'll have 8 sevens, and there we'll obviously have 8 fives and 8 twos, definitely, right? You can do it for yourself. So that means we can assume that we are going to have 8 sevens into 8 fives into 8 twos. So we are going to have 8 70s in this factorial, right? So highest power of 70 is going to be 8, right? This is not 8 into 70, rather this is 8 times 70, 8 number of 70s, that means 70 into 70 into 70. So we are going to have 70 raised to 8 into some number is 50 factorial. So 8 is the answer. Correct? This is one method, fundamental method. The second one is the short method. The shortest method also is based on the fact that in 70 we consider the highest power of the highest prime factor of this number. 70 highest prime factor is 7, so we are going to think only with respect to 7, and the way we do it is we take 50 divided by 7. What do we get? We get 7. We take this number, divide that by 7 again, we get 1. We take this number, we divide that by 7. What do we get? We get quotient as 0. We are only worried about the quotient. Okay, don't see here also we are not worried about the remainder, just worried about how many sevens we can fit. Here we can fit 1 7, here we can fit only 1 7, here we are able to fit 7 sevens, then subsequently we will not be able to fit any 7. So we have these numbers, so we just add them up, what we get is 8, that is the answer. So that is the short method, which is basically the same thing that we are doing here, because if you look at it, these 7 sevens are obviously 7 multiples of 7, so that 7 is come from here, and also there is an additional 7, one additional 7 here that we are getting, that we'll add here. So that additional 7 is this one. So it's the same thing, just that this is much shorter and easy to remember. So thanks for watching the video. I hope you enjoyed this, and I look forward to meeting you in the next class. Thank you.